Okay, so second speaker is Simon Schmidt, and he will speak on quantum values of compiled non-local games.
Exactly. Yeah. Thanks so much for the introduction, and thanks for the invitation for giving this talk. So yeah, today I will talk about compiled non-local games and how to bound their quantum value. And this is joint work with Alexander Kurtle, Julia Mahler-Walter-Honner, who's also here, and Michael Walter. So one thing one can think about is, okay, someone gives you a box, and then he says, well, this is a quantum computer, and you can either say, oh, wow, that's interesting, it's a quantum computer, or you can say, maybe it's not, right? Who knows? And then one way to try to verify that it's actually a quantum computer is, yeah, you're just a classical verifier, right? And now you try to interact with the box, and yeah, after some time you either say, maybe that's not a quantum computer, or you say, yeah, it is. Okay, great. So what can we do to achieve this? Well, so we had some non-local games in this conference, and what you can do is you can play a non-local game, and something that didn't come up yet, I think, is, so there are non-local games that are so-called self-tests, which just means that if I play the game and I win with optimal winning probability, then I can actually infer that the strategy was unique up to some local isometries. So somehow this means I'm just a classical verifier. I play the game, I see, okay, my computer does optimal stuff, and then I can see, okay, it had to be this one perfect strategy that is around, right? So that's one way to verify that the quantum computer actually does what you want. And by combining self-testing with some smart protocols, this can actually be used to verify quantum computation. So if you have some quantum computer, you want to do something with it, and then you verify that it can actually do this thing. Okay, great. So you can trust the quantum computer, and that's it, right? Well, non-local games are nice, but maybe it's a bit, not optimal, because if someone hands you a box and you just have this one quantum computer, then you're like, but I need two, right? So it's two parts. But somehow they also should be very far away because they shouldn't communicate, right? So you have this box, and then somehow you want another box in like another city, and somehow make sure that they cannot interact to do this. So that's maybe not the best thing one would hope for.
And how do you make them share a entangled state?
Another question you can ask. Exactly. I'm just telling you some of the disadvantages, but exactly. And then we can now think about, well, can I do this verifying of quantum computation with a single device, right? Because that's what's maybe the most natural setup. And here the answer is still yes, but now we need some computational assumptions. Because somehow I want to model non-locality in a sense, but if I don't put those computational assumptions, then I cannot do it. But I think computational assumptions make sense because there's still some, I mean, your quantum computer, if you get some quantum computer, it should not have an infinite power, right? So there should be something that a quantum computer can do efficiently in a sense. Okay, but now this new approach, or it can be done, but the approach is a bit different, but still one can ask, okay, we have a lot of nice theory about non-local games. Can we just take our non-local game, use the self-testing stuff, and put it in a one-device framework, right? And this is what we will see, but let's first look at non-local games again. So here we just have two players and a referee, and as I just said, so that they cannot communicate, which is usually enforced by them being very far away. And then they get some questions from the referee, they answer with something, and then the game is specified by some verification function, and the players win if this verification function is won. And then usually the goal of the game is to maximize the winning probability, which is exactly given by this formula where this pi is the distribution of the referee sending X and Y to Alice and Bob. The V is the verification function, and this P is the probability of Alice and Bob receiving X and Y and answering with A and B. And now this winning probability depends on, so this S is the strategy that Alice and Bob agree on beforehand, and now this P depends on the resources we have, right? So, for example, I guess we already saw some, so there are different kinds of strategies, or quantum strategies one can impose or can think about. So the first one is when one just has usually two finite dimensional Hilbert spaces. Those are in tensor product. And now I have POVMs for all inputs, for Alice and for Bob. So POVMs are just like positive matrices, and they sum up to identity. But then there's a second framework where you have the commuting operator strategy, where now the state is just in one Hilbert space. But now I have the POVMs on this big, acting on this big Hilbert space, but now they compute. Okay, and the correlations we get are really, like this. So once it's in the tensor product, and the other is just on one state. And I'm using this bracket notation, but if you don't like it, you just put a comma after the first psi, and then make sure that the inner product is linear in the second part, and then everything's fine. Okay, and it's interesting to know that, so the commuting operator strategies and the quantum strategies, the correlations one can get are the same for finite dimensional Hilbert spaces, but MIP star equal RE shows that in infinite dimensions they can be different. Right. Now so what we said is now we want to take this two-player setup and get it just to one player. So one idea would be, well, I just have one player now, I send him both questions and he answers, but that's a bit strange, right? Because then he has information about everything. But also, okay, if I first send him one question, he has to answer, and then he gets the second question. Well, he still knew the first question, so that's a bit boring, right? So this cannot really work because it's forward signaling, so I just know everything, and then I just can win all the time, basically. So what's the idea? Now we use cryptography to do this. So how do we do this? Well, now instead of sending, so we keep this sequential structure, and now we send an encryption of X to the player. So now in this setup, there's only one player. He gets an encryption of X. He answers with some also encrypted answer of the thing he wants to answer. And the second round is just the same. So Y and B are just the same questions and answers that were there in the nonlocal game. And now the players win if the decryption of the thing that the player answered in the first round, and then X and Y are the same as in the nonlocal game. This is one, right? And how can I think about this? Well, now receiving an encryption of X, I don't know what X is, right? And the point of non-locality is somehow making sure that I have no information from one player to the other player. So somehow he got a question, he answered to it, but he has no information about the question or the answer. And then, well, that's basically the same as I'm now in the second round, so I'm the second player, but I have no information what the first player did, right? We still have to make sure that this actually works, so that the setup translates, but it sounds like a reasonable idea, right? And one thing one has to use is a so-called quantum homomorphic encryption scheme, because if you think about strategies for a non-local game, if Alice receives X, then she picks her projective measurement that is labeled by X and uses this. Now I get an encryption of X. So somehow I also want to make sure that I can use non-local strategies. And this quantum homomorphic encryption somehow ensures that I can still use my, my non-local strategy because the homomorphic property basically says I can work on the encryption without really knowing what the encryption is. Okay. Let's now look at some idealized scenario where we stay in the sequential game, but now we just impose some relations or some non-signaling conditions on the correlation we get from the strategy and see what could be something that we want. So what is a correlation in the sequential strategy? So in the quantum strategy, so I start with a state, then in the first round I make a measurement. So the post-measurement state I end up is this AX psi. But now I do the second measurement after this, so I put this B in between. Okay, now as I said, I want to impose some non-signaling condition. So for example, I could just say, well, I want that this is the same, which just means that, so that the answer of Bob doesn't depend on the question of Alice. But that's not good enough because, so this is just a non-signaling condition, and we know that, for example, for the CHSH game, one can win this perfectly just with non-signaling, but in the quantum setting, it's 85%. So this would not be good enough. And the non-signaling condition we actually want to have or want to get is the following one. So remember before we just had non-signaling with the operators that Bob had, but now we want this to be true for the whole algebra generated by the operators that Bob had. And we will see that this is actually a stronger condition, and it's actually quite nice. And how to formulate it in some C-star algebra language, well, so we can think about this sandwiching by psi xa. We can think about it as some positive linear functional, and then we just say, well, we have some POVMs in some unital C-star algebra and some positive linear functionals. So this phi xa, just is exactly this sandwiching, and then the condition here that it just says that if I sum up over all A, then I'm ending up with some unique state on this C-star algebra. And then the correlation I get is really just I apply the positive linear functional to my Bob operators. Okay. And what we will see, or what is not so bad, is that I call this strongly non-signaling, and any correlation that we get is actually a commuting operator correlation. So you remember we had this quantum strategy and commuting operator strategy. They are the same on all finite dimensional Hilbert spaces. And yeah, what we just see is, okay, imposing this strong non-signaling condition actually results in commuting operator strategies. So how do we see this? So remember we had this condition. We have those positive linear functionals that sum up to one state, and let's say in this specific, so if I put a dot here, then I've defined it like this. And then what I do is just I do the GNS construction with this big state I'm summing to, and then there's a so-called Radon-Nikodym theorem for C-star algebras. So Radon-Nikodym is a measure theory theorem, but if you look at some C-star algebra books, you can see, okay, there's also a C-star version of it, and it basically gives us everything we want. So since the positive linear functionals are all smaller than the one we're summing up to, we can find some positive operator in the commutant such that, yeah, exactly this is fulfilled. So this phi xa of some b is really just the inner product of this mxa pi b. And yeah, since this mxa is in the commutant, it also commutes with pi of byb, and then the only thing that is left to check is that the MXAs actually form a POVM, but they're already positive, and since all those guys sum up to the state, it's also not so hard to show that they sum up to identity. But now, if we look at the correlation, then we see that, okay, I have some vector, I have two POVMs, they commute, so it's a commuting operator correlation. Right? So that's nice. So what our goal will be now is to see that basically in this compiled game setup, this quantum homomorphic encryption scheme does, it enforces some approximate strong non-signaling condition. And from this, we will deduce that actually the quantum value of those strategies for such a game are actually bounded by the commuting operator value of the associated non-local game. And that's quite nice because, as I said, or what we also see, is that we can use all quantum strategies, so just the tensor product ones, in this setup because we have this homomorphic encryption. So somehow we know that, since we can use all of those strategies, then the quantum value, or the least winning probability, will be just this quantum value without the commuting. And now our upper bound is the commuting operator value. But those are the same in like almost all cases, or at least all cases we know. So it's a very nice upper bound. Okay, so to get into this compiled game in a bit more detail. So what you do is, so you have some security parameter for the QHE scheme, and then you first generate a secret key and X and Y questions. So just the questions that Alice and Bob would receive in a non-local game. Then I use this secret key to encrypt the first question. The player now gets this encryption, he answers with some alpha, and the rest just works as before. Okay, so that's nice, and it's some homomorphic encryption, so there are some computational assumptions. So all of this is those are some quantum polynomial time algorithms, which were not touched so much in this workshop. So let's just say those are efficient on a quantum computer. So it's like reasonable computational assumptions on a quantum computer. And the two things I want is, so correctness with auxiliary input, which just means what I told you before, that if I had a quantum strategy in mind, then this eval will allow me to take my POVM I had before and use this eval on this POVM to actually do my quantum strategy, but in an encrypted fashion. And this correctness just makes sure that I can use non-local strategies in the compiled set. But that's not so important for our talk. For us, the most important one is that there's no algorithm that can distinguish two messages, which just means in the first round, the player has no idea which question he got, which makes sense, right? Because that should be similar in the non-local case. Okay, so what's a strategy now for this game? So the strategy depends on the security parameter. So I now have a lot of, but they look very similar to the non-local strategies. It's just that I now have, for every security parameter, I have a POVM for Alice, or this measurement operators for Alice and the POVMs for Bob. And they get better and better, or closer to the non-local scenario, the bigger the security parameter gets. And then the correlation is a bit more ugly, but in a sense it's just the same as before, and I sum over all possibilities that my decryption is A and my encryption is X, right? So it's not so different. Okay. But what we can show is that if we now have such a QPT strategy for a compiled non-local game, and we take some non-commutative polynomial, then there's a negligible function. What is a negligible function? It's a function, so this is in the security parameter, and it goes to 0 faster than any inverse polynomial. So it's just a function that goes to 0 very quickly. So I want to increase my security parameter, and I want that, yeah, this goes to 0 very quickly. And okay, so the one thing I did, because the expression is maybe not so nice, is put this whole expression in one state and just take the trace. But in the end, this is very similar to this strong non-signaling thing, because if this would be 0, then it tells me I'm the same on all polynomials. So if I define the trace of the sigma x1 a lambda to be also positive functional, then it tells me that those are the same on all polynomials, so which is very similar to the C-star algebra generated by all Bob operators, right? So this is already very close to this strong non-signaling condition, but we have to make sure, so we have to use this security parameter to see, okay, we only approach this situation in the limit. Okay. So just a quick overview of what is the difference for non-local games and compiled games. So in the non-local game, I have the tensor product Hilbert space, at least in the finite dimensional setting. And for the compiled games, I now have just one Hilbert space. In the non-local case, I have those. Yeah, sorry.
Can you go one slide back?
Yes.
So, the way the order is phrased, does this eta depend on the polynomial?
Yes.
And is it depend on just the degree or on any, for any individual polynomial you need a new eta?
Let's just say for every polynomial, it's a new one. Yeah, but all of them are negligible. Yes. More questions? Okay, right, so what I wanted to say is just comparing the things. So for non-local games in the finite dimensional setting, I just have local measurements, so Alice and Bob do their things on their own side. Now I have this sequential structure and this imposed strong non-signaling condition from the QHE scheme. But for non-local games, I'm just in an information theoretic setting. Actually, the compiled games, they have some quantum polynomial time. And yeah, the correlations look a bit different, but yeah, it's just very similar. Okay, so now we come to the values of the compiled games. So the goal would be everything I can do in the non-local setting, maybe I can just translate it to this compiled setting by using the procedure, so by using this quantum homomorphic encryption scheme and the sequential structure. And what was already shown before is that if I have a classical strategy for the compiled game, then it will never do better than any, this is the second one, sorry. Yeah, that it will never do better than any classical strategy for the non-local game. But on the other hand, I can also, for every classical strategy in the non-local game, I can find some strategy in the compiled game that basically does the same. So this negligible just says, okay, if I have the security parameter around, then it's just almost the same. But if it tends to infinity, then they just look very much alike. But yeah, the second theorem, so this was the classical case. Now we want to show the same thing in the quantum case, right? And the first thing that you want to show is, okay, I can use quantum strategies from the non-local setting in the compiled setting, which was already done before, which is with this correctness with auxiliary inputs. And yeah, then they basically show, okay, I can just use, or take a non-local strategy, use it in a compiled strategy, and approximately get the same winning probability. Now the question that was left was, okay, can we actually upper bound the winning probability of any quantum strategy of the compiled game? And the best upper bound that one could get would be, I have the quantum value of the game, and then I just add some negligible function, because I can never say for a certain security parameter I don't get a bit better than this negligible function. Okay, and this is our result, which I already said before very briefly. So what we do is, so we take a quantum polynomial time strategy for the compiled non-local game, and then what we can say is that the Leem sup, if we look at all winning probabilities in the security parameter, it's actually smaller or equal to the quantum commuting value of the game. Okay, and how do we do this? Well, the idea is, so now instead of winning probabilities, we have those sequences of winning probabilities, right? Because for every security parameter, we had a strategy and operators. And so we now have to look at this whole sequence and look at the limit of it, because the better the security parameter gets, the closer we should get to the non-local scenario. So what we do is we take a convergent subsequence, and it should just be the Leem sup, because that one can always do. And one problem one gets into is that, well, all those strategies are, so we also have different states for different security parameters, so somehow all strategies live in different Hilbert spaces for different security parameters. And then taking a limit in this is very strange, because you can think that, okay, I increase the security parameter, my Hilbert space gets bigger and bigger, but where should the convergence come from, right? And somehow what we do is we say, well, but it's like functionals on the Bob operators, and those are always POVMs, so positive operator valued measures. So we just take the ones that are on some specific Hilbert space, and we just look at it from the universal POVM algebra point of view. Because, so if this universal POVM algebra, which is just a universal C-star algebra that fulfills all relations of the POVMs, and then I just take the map that sends this universal, so the generator, to the specific one in each lambda, and then I define my functionals now not on the B of H lambda, but really on the universal POVM algebra, and then I'm in the C-star algebra setting again, right? Now I have some positive linear functions just on one C-star algebra, and it's not so hard to show that the norm is less or equal to 1, so I have some unit ball, and then I can use Banach-Alaoglu to actually just go to weak star conversion subsequence of those functionals that are now on this universal POVM algebra. Okay, but then, so weak star convergence basically means that, so it's like pointwise convergence, and then if I look again at this condition, then I see, okay, now the polynomials are in the ease of the universal, so in the generators of the universal C-star algebra, but in the limit, all of this goes to 0. So I will exactly fulfill this strong non-signaling condition. And this means that, okay, sorry. This means, so I took this convergent subsequence with Banach-Alaoglu. I went to another convergent or weak star convergent subsequence now in the functionals, but it fulfills the strong non-signaling condition, which means that the correlations have to be commuting operator correlations, which then means that the convergent subsequence we started with has a convergent subsequence that converges to something that is less or equal than the commuting operator value, because the correlations that come up in this convergent subsequence will come from this from those functionals that fulfill this strong non-signaling condition. And this precisely gives us the result, right? Because now we took a convergent subsequence and we showed that after passing to more subsequences, the limit is less or equal than the commuting operator value. Okay, so that's great. So what can we do with it? So if you remember the first slide, I was talking about, okay, how do we verify that we can do some quantum computations? And I said, well, just use self-testing in some non-local game, and then everything is fine. And now we have this nice upper bound, and upper bounds for non-local games allow us to say, oh, I'm playing optimal, right? Because if I achieve the upper bound, then I can see that I have this optimal behavior, and this allows me to do self-testing then. And what is the standard definition? Like very briefly, it just says that a non-local game is a self-test if I take any optimal strategy and then I find some local isometries that map it to some canonical strategy that I used before. Some of this canonical strategy can be seen as the as the unique one that I had in mind before. But we have this upper bound by the quantum commuting value, so somehow we also want to use the commuting operator definition, or we want to look at it from the viewpoint of commuting operator correlations. And luckily there's also a quite recent definition, which is then called a commuting operator self-test. And this is a bit more formulated in a C-star algebraic way. But now I have a unique state on the max tensor product of the QVM algebras. And actually, so if I have an optimal strategy, so on the right, I have some state and some measurements, MXA and NYB, then they're already determined by this unique state on this max tensor product. And P's are polynomials, so this is actually true for all polynomials. And then, okay, we showed that now we have this upper bound, but we also know games where the quantum commuting value and the quantum value coincide. So we can actually find games where the quantum commuting operator value we can just get by taking usual non-local strategies. So doing this, we can also take a non-local strategy for the compiled game, and then we find some strategies that in the security parameter, they converge to this commuting operator value. And then we actually see that in the limit of the security parameter, the operators of Bob, they really behave the same as the operators of Bob in this unique state of the self-test. That sounds very abstract, maybe for now, but the good thing is, for example, the CHSH game, so one of the simplest non-local games, is actually a commuting operator self-test. And maybe if you know something about the CHSH game or how the self-test works, then it usually says, okay, I have some optimal strategy, and then the operators of Bob, they actually anti-commute. And now what this theorem says is that also in the security parameter, if I look at Bob's operators, then they also start to anti-commute, because if this lambda goes to infinity, then this B0 and B1, they get closer to anti-commuting, right? So somehow this tells us that if I have this commuting operator self-test, then in the limit, the operators behave very similar as the ones in the non-local game. Okay, very good. So what did we do? So we found alternative characterization of commuting operator correlations by considering this strong non-signaling condition, then we proved that those the quantum polynomial time strategies for the compiled game, they cannot exceed the commuting operator value in the security parameter. So if this goes to infinity. And then from this result, we actually found some self-testing results. And I should say that this compiled CHSH game was already used to find some new protocol for classical verification of quantum computation, which was the first thing I was talking about that would be nice to have, right? And that's already everything I wanted to say. Thanks so much.
Any questions or comments?
So I suspect so, but if you have your self-testing result, is this robust?
I guess so this uses the commuting operator definition.
Suppose you know your community operator thing is a robust self-test in a non-local game sense. Can I then also robustly say something about the compiled game?
In a sense, so this is talking about the limit, but I think one has to more carefully work out what's the difference, because robustness and non-robustness in this limit sense. Yeah, I don't know.
So if you want to use this for self-testing, don't you need to know like convergence rates in the security parameter as well?
Indeed. So for a certain class of games, so for XOR games, which also includes this CHSH game, one knows that the convergence rate is in negligible functions. But in general, this is not so clear. Yes. Yeah, so for the specific cases one uses in self-testing, one can usually do it, but in general, we don't know.
Any more questions? Actually, I have one question. So when we do the compiling, can we just use the classical homomorphic encryption? Or we can actually prove that it's not working?
So the classical homomorphic encryption, the problem is that you want this eval to work on quantum circuits, right?
Oh.
Because somehow you want to make sure that you can use the POVMs from a non-local strategy also in the compiled game. And for this you need some quantum homomorphic encryption.
So at the stage of evaluation we need something quantum.
Yeah.
Okay. So this the continuing question is it somehow realizable in the laboratory? The quantum homomorphic encryption.
That's a good question. Yeah, I don't know.
Oh, okay. So yeah, I'm just asking because the classical homomorphic encryption is something we can really use right now, and maybe we can do the test.
Yeah, that sounds good. Yeah.
Okay. So any more questions? Yeah.
Schmidt, you have a simpler compiler too, also.
Yeah.
So I guess my question, my loaded question is, do we need all of QFHE to do a compilation, or is there some simpler primitive that could potentially?
Right. Yeah. So
because we're not using the full quantum suggested by your question, like, we're not sending quantum messages or anything like that, which in QFHE it's kind of built to do, so it's kind of overkill.
Right. Yeah, we have something more recent which doesn't use this QHE scheme, but rather some, let's say, remote state preparation in the first round, which could lead to some weaker, or which should be a bit weaker on the cryptographic assumptions. But how one can use it like in practice, I'm still not sure.
Okay, then let's thank the speaker once more.